Okay, so as we continue to build our understanding and catalog of forces, we're going to dive back a little bit and talk a lot more in depth about friction. And friction is it's a very relevant force in all aspects of life, because friction is something that typically can't ever be ignored. It always opposes motion. It's always slowing things down. It's the main reason why things come to rest. So we're going to take a look, more in-depth look about friction right now. So in this pre-lecture video, he talks about the different types of friction, but the main thing is actually popping up right now. The main thing that you need to remember is that friction always opposes motion. It's always in the opposite direction. So if I'm moving to the right, then friction is acting to the left. Now we're going to dissect each type of friction a little bit more in depth, but he goes through and talks a lot about the difference between static friction and the difference between kinetic friction, and how these two are very similar yet very different. And the main things to remember is that static friction is stationary. Don't know why I did it like this. And kinetic friction is in motion. Okay, so we'll talk a little bit more about these in this segment. All right, so now in 5.5, we're going to talk about friction. There's three types. We have static friction, we have kinetic friction, and we have a brief introduction into rolling friction. Now, all of these have the same general formula, but we'll talk a little bit more about each type in this segment. So in class, I'm gonna do a little demo, and I'm gonna use a force sensor to measure how much force is needed to pull a cart. And I have a few different extensions of this. I start to pull a cart, to start pulling it, and then how much is actually pulling it. Then I change the cart to on its side. Then I pull a different type of a cart, and I'll talk about that. And then I pull a heavier cart. And so I'm going to do this in class, but I also want to take a brief minute just to talk about the different graphs that we get. So the real, or the first one, I guess you could say, is the red line. And the red line, it might be a little hard to see, but it's on the bottom right here. And this is just 3 masses on a felt cart, and the felt is on the lab surface, the lab station, and then I pull it across. And when I look into all of these graphs, they all have this general trend. And I can see it best probably in the purple one, because it's the biggest, but I start pulling, and I start pulling, and I peak, and then I drop down. And this is the concept of what is the difference between static friction and kinetic friction. So when an object is at rest, it's under, and you start to pull on it, it's static friction. But eventually, you have to break that static friction to get it in motion. So we see that general trend. But now I'm going to look at a couple other things. Now I have this blue line, and the blue line is 3 masses, still 3 masses on the side of a cart. And we notice that for the most part that these are actually identical. So friction is not a function of the cross-sectional area that you have it with. And it's kind of a weird concept, but if I have less area, there's less in contact, but there's also more force acting in that smaller area. So I'll talk about that a little bit more later. But then we got this green line, and this green line represents 3 masses on a cork cart. So the difference between, if I could imagine like cork versus felt, felt's a lot smoother, so there's a lot less friction. But then also I have this orange line, and this orange line is even a little higher than that, and the orange line is 6 masses on a felt cart. So if I have more mass, I also undergo more friction. And that kind of makes sense too, right? Because I'm pushing down on the surface harder. And then finally, I have, in purple, I have 6 masses on a cork cart. So we see that as the highest amount of force needed to get this thing in motion, because it's got the most amount of mass and it's got like the roughest surface. So we'll see that in class, and hopefully we'll be able to build some connections with that. So the first type of friction that we're going to talk about is static friction. And here, as we talked about before, here is somebody that is pushing on this box. So this girl is exerting a force. There's definitely a force being exerted, but the box isn't moving. So whatever she pushes forward with, static friction is pushing back with. So static friction is the force that a surface exerts on an object to keep it from slipping across the surface. If I imagine putting something on an incline, right, gravity's pulling it down. If it's not moving, static friction is keeping it up. If we ever need to find the direction of the static frictional force, we kind of go in the direction that the object would move and make it the opposite. So the static frictional force will go in the opposite direction. So it always opposes the applied force. So in this example, this person's pushing on the box. The box is pushing back because of friction. There's a frictional force from the surface that's pushing back. So this is in static equilibrium. The box isn't moving and it's not accelerating. So the static friction force, therefore, has to be equal and opposite to the force of the push. The question is, what if she pushed less hard? Well, then her force of the push would be a little less. But if we're still in static equilibrium, then the static force must also be a little less. So that gets a little confusing because now I just said I changed the magnitude of the force. So let's take a look at what those free body diagrams would look like. So in the first example, A over here, we have a person pushing gently, and we see that the forces are balanced. If the person is pushing harder but still not moving, the force grows, and so does the force of static friction. And then eventually I'll get to a point where I can push the maximum amount that static friction can withhold. And if I look back with the first graphs that I have, that's what this graph looked like. It was this, and then it came down. We're talking about this maximum amount, and that is this maximum amount of static friction. So static friction, the harder and harder you push, the harder the friction pushes back until you reach its maximum possible magnitude. And that equals, there's a formula for that. It's mu s times the normal force. Where mu s, so this is the Greek letter mu, it's called the coefficient of static friction. And that depends on the surface. And we're going to do a lab about that on tomorrow, essentially. So the direction of the static friction always opposes motion. The magnitude has to adjust itself so that the force is zero. The net force is zero. So the force of static friction can increase and increase and increase until it reaches its maximum value. If it's greater than that maximum value, the object will slip and start to move, and then that leads us to the concept of kinetic friction. So static friction, a very, very difficult to understand concept for people that are new to friction, but and it's a little frustrating, but we just got to remember that the static frictional force changes based on how hard you push until the object starts to move. And once it does start moving, we do get into kinetic friction. And kinetic friction is much, much, much easier. Kinetic friction has a constant magnitude that's equal to the coefficient of kinetic friction times the normal force. So in this case, this woman is pushing the box. There's a push exerted. The force of kinetic friction is opposite of it. The net force is zero. We're going at a constant velocity. I can also, I demonstrated this in class, I can also push the box fast. And my free body diagram is actually identically the same. Remember, forces don't talk about velocity. Forces never talk about velocity. Net forces have or go to acceleration, not velocity. I don't know why I did that. There's velocity. Here's a red line, not velocity. So even though in this case she's pushing faster, the net force is still zero because the forces are still balanced. So there's also this concept of rolling friction, and this is a very difficult kind of thing to think about, but it makes sense. When a wheel is rolling on a surface, there has to be some type of friction. The wheel is pivoting around a point. Kinetic friction has to deal with the sliding of something across a surface. So that's actually not a good representation. There is a small part of the wheel that is contacted to the surface that is stationary with respect to the surface, so it's not sliding. So instead, we call this the interaction between a rolling wheel and the road. We call it its own type of friction called rolling friction. This will pop up extremely little in this class. It's just a different way of thinking about it. We worry just mainly about kinetic and static, but there is a small little extension known as rolling friction. Okay, so in each of these examples, we saw this mu with a subscript, and those are right here. These are coefficients of friction. And all that means is that if I have a surface and another surface, how they interact with each other is actually constant. So for example, if I have rubber on concrete, the coefficient of friction for static friction is 1, and for kinetic friction is 0.8. You will see 100% of the time that static friction, the coefficient of static friction, is larger than the coefficient of rolling friction, or I'm sorry, kinetic friction, because it takes extra force to get something in motion, but an object in motion tends to stay in motion. So once you get it in motion, then we get into kinetic friction, and these coefficients are always less than the previous example. Always, 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 always. And again, that goes back to that graph where I had like a peak and then it drops down. This is F static max, and I can solve that with these coefficients of friction. These are not anything that you will ever have to memorize. You will always be given them, or technically you can also solve for them if you have other information. But those are coefficients of friction. In our lab tomorrow, we'll deal with taking a look at different types of coefficients of friction for different surfaces. So to give you a quick little summary here, these are the formulas for each of the frictions. Now the easy ones, kinetic, kinetic, we have the coefficient of kinetic friction times the normal force, and it opposes the motion. Rolling friction, exactly the same. The complicated one, and this is where people struggle, is static friction. Static friction has some magnitude that is equal and opposite to the force that's being applied, which is less than or equal to its maximum static frictional force, which is equal to the coefficient of static friction times the normal force. And again, this one's complicated. I can push harder and harder and harder, which means that the force opposing my motion gets larger and larger and larger until I reach this maximum static friction, and then I break it and go into kinetic friction. But the maximum static friction is the coefficient of static friction times the normal force. Again, it's complicated. It's a weird thing to wrap your head around, but it's true, because there has to be no net force if there's no acceleration. All right, so let's jump into a quick little example problem here. And we have, does it move? So we have a box with a weight of 100 newtons is at rest. It's then pulled by a 30 Newton horizontal force. The coefficients of friction are labeled on the diagram. I have static friction and I have kinetic friction. And I want to know, does the box move? Well, if I need the box to move, then I need to break static friction. So really my question is this greater than or equal to F static max? I'm not sure that I put the equal sign. Yeah, I put the equal sign in the right spot. Okay, awesome. So in order to break static friction, then the force applied has to be greater than F static max. So the force of static friction max is the coefficient of static friction times the normal force. The coefficient of static friction is 0.4 what? Well, oddly enough, a coefficient just relates to the surfaces that are in contact. So anytime we have a coefficient, it's actually dimensionless, aka unitless. And the normal force in this case, we're on a nice flat surface, so that's just going to be equal and opposite to the weight. which is mass times gravity. So the mass is 100, oh, well, actually, we can just leave that as newtons, right? It's already in 100 newtons. So that means that it's 40 newtons. So the maximum static frictional force can exert up to 40 newtons. I'm only pulling at 30 newtons. So my answer is no, the box does not move. And it doesn't move because it doesn't break static friction. Now, a follow-up question was, what if the box was already in motion? Well, similarly, this coefficient of kinetic friction here is 0.2, which means that the force of kinetic friction is 20 newtons. So if the box was already moving, because there's 30 newtons over here and only 20 newtons over here, it would continue to move and actually start accelerating because the force is greater than, the force applied is greater than the force of static friction. I'm sorry, kinetic friction. All right, so we got a partner problem that we will, of course, do in class. But this gets into this concept of you've probably seen them maybe advertised before, but furniture sliders or sofa sliders. So Carol's got this 32 kilogram sofa, and she wants to move it. So she used these sofa sliders with a coefficient of kinetic friction of 0.080. Again, no unit, on the carpet, under the feet of the sofa. She then pushes it at a constant 0.4 meters per second across the floor. How much force does she apply to the sofa? So we'll take a look at this example problem in class, but we're just essentially, if she's pushing it at a steady speed, right? That's what it says, a steady speed. That means that this is an equilibrium problem. But if it's in motion, it is a dynamic equilibrium problem, and it'll stay in motion. And we'll take a look at that in class. If you want to take a look at the free body diagram that I just talked about, it's this guy right here. But like I said, we'll take a look at it in class. So one last little concept is what actually causes friction. And friction, you think if you have things like ice on ice, you think that friction is essentially zero. And it does. It does get really close to zero because ice is a very smooth surface. But all surfaces at a microscopic scale are actually very rough because of the random molecules and alignment of that. They're actually very rough. So when two objects are placed in contact, if I look at my picture here, there are some points that jam against each other, and that causes resistance. So friction is just that. It's the resistance that two surfaces have with each other. So actually, ironically, these are Mizuno shoes right here. And Mizuno, if you're interested, M-I-Z-U-N-O, Mizuno makes probably the best in the business for volleyball shoes. And when you think about being on a gym floor, your surfaces are going to be a little bit flatter and you slide around a little bit. So when you get good athletic shoes like Mizuno shoes, they have extremely high coefficients of friction because of the design on the bottom of them, and that allows you to get much better traction. And then with better traction, you can get greater acceleration. So people need and have to have good shoes when they play sports like basketball and volleyball because it gives them good traction because of the rough context between the surface and the shoe. All right, so we got a quick check here. Box is being pulled to the right. The tension force is greater than kinetic friction, so the box is speeding up. But then suddenly, the rope breaks. What happens to the box? Well, we know that there's still friction opposing the box, kinetic friction. Once I get rid of the tension, the only force acting in the X direction is friction, and it's acting opposing motion. That will cause the box to slow down and then eventually stop. Okay, so it doesn't keep its speed for a while. It's gonna, as soon as I lose that tension force, it's done accelerating. It's done getting that force driving it to the right. So it's instantly gonna start slowing down. It won't stop immediately because it will take time to accelerate. Now, if you have a really high coefficient of friction, that'll lead to a really high acceleration, but it doesn't stop instantly. All right, so we got another partner problem that we'll take a look at during class. This one is actually pretty complex, and I love solving it because of how complex it is. And it really brings together kinematics and dynamics. But we have a car is traveling at 20 meters per second, and it stops at a distance of 50 meters. Can I do anything with that? Yeah, you bet. I can find the acceleration, right? Assume that the acceleration is constant. The coefficients of the friction between the passenger and the seat are 0.5 and 0.03. And my question is, will a 70-kilogram passenger slide off the seat if not wearing a seatbelt? So this is actually a really important concept. Why do we wear a seatbelt? If we have a drastic change in acceleration, I need something that's going to keep my body in the car. And we've all seen videos or pictures or whatever of people that haven't been wearing their seatbelts and are involved in high-speed collisions. And if they don't wear them, you can get launched through the windshield. And the reason is an object in motion tends to stay in motion. So you being in the car, if the car is traveling 20 meters per second, you are traveling 20 meters per second. Okay. That being said, you're sitting on a seat, and that seat also has a little bit, not much, but a little bit of prevention for you sliding forward. So actually, it says here the coefficient of kinetic friction. I don't need that. Okay. I'm just curious at, given this acceleration, whatever this acceleration is the force that's causing that acceleration greater than the force of static friction? And if it is, then I will slide off my seat. If it's not, then actually I'm safe. Now, I'm not telling you to not go home and put your seatbelt on. I'm just saying that there is a limit to this acceleration, and if you're under that limit, if your acceleration is small enough, then static friction by itself is enough to prevent you from moving. And if I think about that, that kind of makes sense. I'm trying to think of some real life examples where, like, let's say you're on a sled, right? When a sled's moving to a stop, you don't instantly slide off the sled. But if your sled hit a tree, you might go flying forward, okay? That's all I'm trying to say. So we'll take a look at that problem in class.